Hello everyone. We'll start the session for week two. And this is Subrat, and I'm a third year PhD student at IIT Delhi. And currently, I'll be tutoring this course, Deep Learning for Computer Vision. And this is the week two of our live session. And last week we had a session here in the same time about the week one content, and we'll be having the same for week two as well this week. Yeah, so I'm a PMRF fellow as well, and we're doing this live session weekly uh, for every week till the end of 12 weeks. And we were waiting for others to join, but I guess these are all the people who will be joining today. So let's just wait for 2 more minutes, and if no one joins, we can start the session and go forward with it. Okay, great. We'll wait for 2 more minutes. Yep. We can start now, I guess. I guess we have about 13 members, uh, 13 members excluding me. So we can start now. Anyone unmute? Yeah. So, so we'll start by discussing what are the contents that was discussed this week's lecture. So we'll be discussing all the stuffs that was discussed in the week two content, and the week two started with uh, sort of uh, making meaning out of the raw image. So in this week we saw that so if you went through the lectures, you must have seen that how we can sort of extract certain features and certain uh, characteristics from the image, like edges and blobs, then corners and all these things. And this week sort of gave us a way to explore image more and trying to extract some meaningful properties and meaningful features out of the image. And so this week started with a little bit discussion on what happened last week about the convolution and about the features and how a image is represented and how a image can be uh, like modified and all these things in the week one. Then the discussion started with the edge detection, where where Professor Vineeth discussed about how how we can extract sort of edges in different directions, in vertical and horizontal directions, and how we can again um, uh, glorify the edges and make it more clear and make it more complete, and also how to get meaningful edges, not just every edges in the image. That was this the so that was like first lecture when we discussed about edges, and then Professor Vineeth like went into like blobs and corners and all these things, and at the end, so he discussed about the shift, shift and other feature detectors, and shift is a very powerful detector that was that discussed about shift invariant feature transformations. And with that, like this week's content is like was over, and so what we will be doing in this live session is that, so we'll pick up some portion of the all the topics that we discussed that were discussed in the course. So will not be discussing everything. So as like last week, so I was told that we should be picking some topics, some key topics from this week's teaching, and we'll be discussing that. And after discussing that, we will be solving some code examples that was given by the professor. And I can also share you the link of the code where you can, which you can take and which you can run it and sort of uh, try to get output out of it. So it will give you a edge towards practical implementation of what you are reading as in as math equations and all. So that will be the part two of this live lessons. And so before starting this live session, so if you, I just wanted to let you know that if you have any doubt while I'm explaining something, or if you have any doubt from the session, you can directly ask me in the chat window itself, or if you want to speak, you can just raise your hand or on and unmute and speak. And so that is about like how to like how the session will be. And if I could not answer your questions, I'll note it down. I'll try to answer in the next session, or if I still could not get the answer, I'll take it up with Professor Vineeth and get back to you as soon as possible. Okay, so with that, we'll be starting our session today. Okay, so I guess there are 17 members, much more than last time. Great. So I'll be sharing my screen now. So is your screen visible? Can someone comment in the chat or tell in the mic? Is my screen visible?
Yes.
Yes.
Yes, your screen is visible.
Great. Uh, okay, great. So so we'll start by discussing about, yeah. So this week we started with so this week we started with edge detection, and so let me turn. Yeah, so edge detection, and so edge detection started with this discussion that given an image, so how can we sort of extract edges out of it? So that's the only goal, and how they are generated, how they are detected. So we'll discuss, and so uh, the fast way of sort of detecting this edge is calculating the maxima and the minima uh, of this image. So let's say so if you define, so let me just take you to this screen, my notebook screen, where I can specifically tell you about this. Yeah. Okay, great. So we'll be discussing edge detection today, because as one of the candidate topic to be discussed this week. And so let's say, so what is an edge? So if we put it formally, uh, if we put it formally, like let's say this is one image, This is a image, and let's say this image is like this, just black and white. We say that if there is a sudden change in the intensity of the image, like this, here to here, this boundary from which this sudden change has occurred is called is called a uh, edge, and all these things are covered in the lecture. So I will not be covering it in very detailed way. I'll be like covering it in a superficial way, and if you have doubts you can ask and we can discuss about that as well. So this is a discontinuity in image, where there is a rapid change in the intensity of the image, or you can say there is a rapid change in the intensity function. And so what will happen is that, so if we plot the intensity graph of this corresponding image, it will be like the intensity is low around here. Let's just, yeah, low around here, and suddenly it's low around here, and suddenly at the point of zero, it's getting increased and then constant again. So what they're saying is that to detect this like sharp increase or sharp decrease, what we can do is that we can sort of so this is, let's say, the intensity function f. What we can do is that we can capture the f dash. So what f dash will do is sort of take the derivative of this curve, and take the derivative first order derivative of this curve, and it will turn out to be something like this. Yeah. So this is the sort of the derivative that you get when you differentiate this above function, and they say that the maxima is the point where there is an edge. They said that there is a maxima. So they say that at the point of the edge there will be maxima. So what people do is that they sort of take this and sort of try to take one row of it. So this is one row of the image, and this is 1D. Okay, so this is 1D, and if you take intensity of this image across x-axis, it will come exactly like this. The f will be exactly like this, and exactly like this, and so if you differentiate that, you will get a maxima like this. Oh, sorry, so this is not like this. This is like this, and the f dash is like this, and this is a differentiation across x. So I can say this is df by dx. Sorry, this is f of x, and this is df by dx. So sort of what I'm trying to say, and you can say at this midpoint where x equals to 0 is the maximum, and this is the point of maximum. Okay, so this is the point of maximum, and when we think about it, it also makes sense that when there is intensity change, there will be edge. So what about images like this? So there's an image like this cup, and if you look carefully, it doesn't look like this to have a very sharp change. But if you zoom in some portion of it, you can see that A line is basically like this. There is a dark patch in between, and there is an intensity shift from here to here and here to here. So there's the basic idea behind like detecting edges, and so since we're just dealing with the images, we shouldn't be we shouldn't be dealing with the gradients as such. So we'll be dealing with the filters. So let's say this filter. Let's say this filter is so let's say this is the operation to get our these edges, and we have to design a filter that corresponds to this operation. And that filter, so let's say for this, the filter will be like this. This will be same as taking a gradient and taking the maximum. But so if you want to detail like why this filter is like, if I take this filter and make a convolution of across the rows of an image, and I will get the maxima, so I'll get the edges out of it. Then you have to refer to the lecture number 1, where sir has discussed about like how a derivative can be written in a simpler form, and is equivalent to just convolving a -1 and 1 filter across the image. So if you have any questions so we'll discuss about these filters in the later slides as well. So if you have any questions about like this general idea of edge and how to detect edge, you can ask me now. Like you can always ask in between questions, like in the chat and all. But yeah, so I'm just giving you a dedicated slots because um, from this point, I'll assume that you have a basic idea of edges and how edges work, and I'll not be able to like I'll not be going to discuss that from the scratch again. So if you have any questions, you can put in the chat, or you can just speak up by unmuting your mic. Yeah, you can make this as an interactive, like if you are willing to ask questions, or like it will be better. Like I mean, I say like what happened last time. Also, some people couldn't watch the videos, like they were not able to watch the videos as such in the week. So for them, I would say that like if you have any basic doubts as well, like whatever you have watched or something, you can ask that as well. Or if you haven't watched any video, like I will discuss some of the stuffs here, you can go back and always look into those videos and tutorials. But after 2-3 weeks, like if you have skipped all those videos, that keeps getting piled up, and you'll never be able to complete that. So even if you haven't watched, you can just ask from the discussion today, like, what is this edge? Or, I mean, how we're computing that, and we can have a discussion on that. Then you don't have to watch it again. Or like if you have if you're understanding what I'm trying to say, you can put in the chat as well. I'll know that you have understood. Like just put we understood these concepts.
Hello,
Hello,
am I
hi.
audible? Yeah.
Yes, yes.
Sir, I have a doubt. Maybe I am new to this area. Like, may I know how did you plot that image like EF and EF dash?
This one.
Yeah.
Okay, so this is the intensity plots. So in the last lesson we discussed about uh,
Balasubramanian. Basame.
yeah, I muted him, I guess. Yeah. So in the last lecture we so so do are you familiar with representing images.
Hello?
Yeah, are you familiar with how you represent images in like
Yeah,
numbers?
with respect to intensities, yeah,
Yeah, yeah. So
matrices.
yeah, great. So then this is just like just the intensity plot. So this f is a function of intensity. So I should put fi here. So we're just plotting the intensity. Here the intensity is like 0, and here the intensity is 255. And if I normalize that, it will be 0, it will be 0 and 1. So it's just plotting that. I can put 1 here as well. So I'm just plotting the intensity of this pixel, and I'm sort of looking for a point where the intensity is, so intensity is going through a maximum change, or I can say the gradient is the maximum. The change in the change in this direction is maximum. So so that's why I took the gradient of this plot of the intensity plot, and I choose the point where there is a maximum, the maximum of the gradient. Does that make your question clarify?
So means this x-axis is, matrix indexes, right?
No, no, no. So I'll just tell you. So what I plotted here is just for one row. So this is a image. Let's say there are n row and n columns. What I've done is that I have taken all the n columns and just one row. Okay. So in one row, the pixels will be from 0 to, let's say 0 to n. So there will be pixels from 0 to n, and each have just one value. Each pixel have just one value. So what I've done is that I have taken first pixel's value I plotted here, intensity value, second pixel's intensity value plotted here. Like that, I plotted all these pixels from 2 0 to n. Yeah. Is it clear now? Like what I have done? So these are the intensity plot of one row. Of course, it will be same for all the rows, but yeah, it's just one row. Yep. Any other questions? Like, if you have understood, also you can put in the chat that you have understood this concept, and we can move forward. Okay, great. So we'll now discuss something that is called Sobel filter. Okay, so I have a question. What is the necessity to take differentiation? Uh, we have to take differentiation to see uh, the change in the intensity, because what happens is that this is a fairly simple image to see, and what happens is that this sudden drop in intensity or sudden drop in this intensity in image was not that simple. Some images are noisy, so in the noisy image, the intensity curve will not be this smooth. It will be coming like some zigzag line like that, and uh, uh, it is not very efficient to find this rise in or a drop in intensity, uh, drop in intensity like effectively in that noisy images. And also there is this color shift, and there is and sometimes what happens is that there is like a space shift, and we find the edges such as like suppose there is a staircase in the image of a staircase like this. The colors of the stairs will be same, but there is a orientation shift in the stairs, and that lead to some shadows in this area. So those are also like detected by, if we take gradients and all, but it is not detected if we just look into the intensity graph. And also, like all these things are, we assume that we're taking one row at a time, but if we apply like 2D filters, so this is like just evaluating the image in one row. So if we evaluate, so let's say the image is like this. When sort of evaluating it in with a 2D filter like this, and instead of um, talking about only one change in one dimension, we're talking about in 2 or 3 dimensions. Then um, uh, taking a faster derivative of this thing, and finding the maxima in the 2D space is much more efficient than just looking for a sharp rise or fall in the intensities. Uh, and what happens is that sometimes the intensity is like this. So the intensity will blur out from this. So it will be black, and suddenly it will be blur out. So there is no edge here. But if you plot this, it will come as like this. I mean, there will be a shift in the intensity, but it will be a smoother shift. And how smooth or how far, how sharp, how like spiked a intensity curve is, it's not actually easy to measure because you have to define a lot of parameters for that. That's why we just do this. I hope that is clear, and we'll be moving forward with our discussion in the slides. So what happens is that we sort of try to find maxima and minima in the, yeah, sort of try to find maxima and minima in this um, uh, maxima and minima in this uh, in the gradient of this intensity, and we'll find minima if there's a sharp fall in the gradient, a sharp fall in the intensity in the image, and there is a edge. So there is maximum and minimum, and there is a second order derivative as well. So we sort of try to find second order derivative of the gradient plots to sort of clearly find the edges. So what we do is that so this is first order derivative, and then we take a second order derivative of this, and it looks like this. Sorry, so this will look like, so it is increasing, so the increasing, so it's okay. And okay, and we say that when there is a zero crossing, there is the maximum, and there is the edge. So here there is a zero crossing, and I can say it is a point of edge, and here the this is maximum, and here it is minimum. So here it is maximum, and here there is a edge. There is an edge. That's why I put we put here that if there is an image, and so to detect the edges, we have to find the maxima and minima in the first derivative, or we can go a step further and do the second derivative to get the zero crossing. And where there is a zero crossing, we can say that there is an edge. There is an edge. So one of the like popular operator that we saw in the lecture as well is the Sobel operator. So Sobel operator sort of so the way we discussed 1D filters. So similarly, we can design 2D filters and 3D filters as well, and we can do this by using different types of sort of uh, filters. And so this filters, so what we discussed, taking the first derivative and second derivative, is sort of uh, uh, like saying, using first order derivative we can find the edges, and or we can using second order derivative we can find the edges. So then what we did, so actually, so I'll just discuss here that, so this first order derivative is something we are using to find the edges, but in an image we cannot apply this. And all you can do is that we can, this is really costly. What we can do is that we can just take a filter and do the convolution around it. So we can take a filter and sort of do the convolution in the image. Since we are doing that, we can design sort of different filters to detect different uh, things like vertical edges and horizontal edges and corners and all. So since we are doing that, since we are doing this parsing of the image using our filters, so it is crucial to design this filters very carefully. And if you have seen this lecture, you can say that what two uh, these two filter do. So how they created this filter? So this is for 1D filter. You can expand it to make it a 2D filter as well, -1 -1 1 1, or you can you can analyze three blocks as well simultaneously, and you can design a 3D filter as well, where it will look like this, and it will be able to detect your edges and corners and everything. So it's just that, just remember that we sort of started discussing about edges. Edges are a sharp change in the intensity. So after edges, we say that to detect this, we have to do the first order derivative, and we cannot do the first order derivative while like doing it in the image in the computer. So we did this. We designed this filter where we'll use this filter to convolute across the image, and we say that this filter convoluting this filter across the image is similar to taking the first order derivative and getting the first order derivative and pointing out the minimum. So that is the way you discussed. And since we discussed about one dimensional, you can expand up to two and three dimensional. Yeah. And so these are like these called Sobel filters, which is three-dimensional filters. And if any one of you can tell me in the chat or like in the mic, what this filter do, like any idea, like what this filter do, what is this GX2 and what is this GY2? Great. So also this GX sort of detect these vertical edges, and GY sort of detect these horizontal edges. And if you have seen Professor Vineeth's lecture, he said that if you take the filter and if you plot it, you take the filter and if you plot it, it should look like what are the what property it is sort of trying to extract. So if you see the first filter, it's something plus, something zero, something minus. So that means the intensity is decreasing. So it will be like black, then white. So if you plot this, you can see clearly, even if blurry, this represents a vertical line. And similarly, if you plot the gxy, it will sort of look like a horizontal line. So gx sort of creates this uh, gx sort of creates this vertical sort of filter out the vertical lines out of the image, and GUI sort of filter out horizontal lines out of the image. Or vertical and horizontal edges out of the image. And and this Sobel operator is so we this operator like this star sign is something we use to denote the convolution. So we convolute our gx filter to filter all the edges, and GY to filter all the horizontal edges, and the magnitude of this can be calculated using this gx square by gy square whole root. This is a simple thing that we do to calculate the magnitude of any vector, and so, and this is the the theta is like the angle. This this is like making the edge is making towards from the base. So it's like finding the edges towards the right, edges in the vertical, and edges in the horizontal, and edges. I mean the angle between the edges to the x-axis of the base of the image. So yeah, so this is the Sobel operator, and if we apply the Sobel operator on this image, you can see this is the Sobel y direction, and y direction creates all the horizontal edges. So all the horizontal edges are somewhat horizontal, and if you see Sobel x direction is something that create the vertical edges, and if you see this leg of the table, this edges is clearly defined here, but not here. If you see these lines, since they are horizontal, are defined here, but they are missing here in the horizontal filter. So we'll see in the code how to generate that and how to apply these filters. And if we take the root of like this, like if you take the square, and if we take the magnitude of these two vectors, we will and add that, and we'll get this image where we can find all the edges. Yeah, all the edges clearly, like it will be it's kind of a combination of these two. And yeah, here's the final output that you can see while detecting the edges. If you have any questions or something, like you can put it in the chat. And like if in when you have like in one of you has a specific portion or like part of the subject where you have doubts, you can ask that as well in the that regards to the edge detection that was discussed in the lectures as well. Okay, great. So we'll be discussing next the shift operator. So the shift operator was used to find the key points in an image, the important key points in an image. The application of shift operator is that given two image, and one image is the original image and second image is a transformed version of the image, such as horizontal shift or vertical shift or any sort of shift in the image. The task of this shift operator is to like find the key points in these two images. So what happens is that, give me a moment. Yeah. So what happens is that, let's say we have an image and we sort of now detect the edges or key points in an image. So what if the image is now shifted to right by 1 pixel, or let's say rotated by 30 degrees, or it is blurred a bit. So is it possible for us to, is it possible for an algorithm to detect same portion of the object or the same portion of the image in the two images? For example, let's say in this case, this is the leg of this chair, and this is the leg of this chair in the another image. And let's say this is a rotated version of the image, this part. And so the question is that, will the shift algorithm be able to detect this person in this image is this person in the rotated image? Like, will it be able to detect that? So the answer is yes. The shift was very the shift algorithm is very was very much successful, and it was created around like 19 no 2004, I guess. The shift was created around 2004, and it's almost 2 decades, but the use of shift has been increased in the past. So far they have like 50,000 citations, so that tells us about the popularity of shift uh, in the computer vision domain. So yeah, so it's a pretty fundamental operator. Uh, it's a pretty fundamental operation to do in an image. Yeah. So the full form of shift is that this scale invariant feature transform. So so there are 4 steps in that. So sir has discussed very uh, broadly in this topic. If you wanna know about this topic more, you can always refer to the lectures that were provided by the NPTEL, and you can get all those things in detail. But today we will be discussing these things in a very brief manner, where I'll be just talking about all the stages that uh, uh, an image go through before sort of getting analyzed by the shift, and sort of trying to figure out the key points in an image. So, so there are like majorly 4 steps that involve in the shift, which sort of creates, which sort of uh, uh, give give us the uh, our required thing. So first is the scale space extrema detection. So which is detecting the interesting points. in an image and which should be invariant to scale and the orientation. And this is achieved by the dog, or that is called difference in gradients. So you should mark the key point that invariant to scale and orientations. So these interesting points should be invariant to the scaling of an image from 1x to 10x, and the orientation of an image, like if the image is originally in the 0 degree, and if you rotate it by, let's say, 30 degree, these key points should be intact. Like the key point this algorithm detected for the raw image should be same as the key point the algorithm detects in the shifted or the rotated image. Moving forward with the steps, step 2 is the key point localization. Um, so let's say uh, the candidate location where you sort of mark that there is an interesting point that might not be actually a point, that might be actually in between two pixels, or um, the location is not clearly defined. So that's why in the key point localization, we sort of localize these key points in the image and determine its location and scale at each candidate location and select them on the basis of stability. If we see if some interesting points are not that stable, we'll discard that and keep the only ones which are stable. Third step is pretty simple, like orientation estimation, where we use the local image gradients and um, we sort of assign the orientation to each localized key point. So uh, it's just saying that so in the direction of maximum change, there is a like the gradient faces in that way, and if we can if we can find the face of gradients in the modified image, you can say that how much the image has been rotated or something, or shifted. And the fourth one is key point descriptor. Uh, uh, so this key point descriptor sort of extract this local image gradients at a selected scale around the key point, and uh, and this it uses this to form a representation that is invariant to local shape and illusion distortion. So it's like creating this image gradients, and uh, so we sort of create this image gradient around the key point, and form a representation which will be invariant to all this shift and scale. So before like going detail on this, like I'll just try to dissect this term in the step one, scale space extrema detection. So we're sort of taking spaces that are scaled and trying to detect the extrema out of it. By which I mean, so scale space is something we wanna compute. So we will compute the scale space by uh, uh, 1 second. Yeah, we'll compute the scale space by this Laplacian difference of not difference of Laplacian by the Laplacian, and uh, this is achieved by creating the dog or the difference of gradient. So what we do is that we sort of create this scale space. So by scale space, what we say that, let me actually recall that specific formula that was used in the lecture to define these, like to compute the scale space and to uh, take this Gaussian around it and to uh, take difference. So let me just grab that slide for you so that it will be efficient for me to show. Give me 2 minutes. Yeah. So the scale space is like sort of what we do is that we convolve the Gaussian filter across the images. So to put it in that way, what we do is that we take the Gaussian filter with the standard deviation of sigma and we convolve it around the image. So remember what I said about this noisy image. So when there is a noisy image, we have to provide, so we have to do Gaussian sampling. Or what you can say is that we sort of take this Gaussian filter and move it over the image to sort of get this um, a smooth version. So this is the mean, I guess, of the standard deviation of the Gaussian of this Gaussian function. So it's like thing like this, and what we do is that we create an octave. By octave, what I mean is that we sort of change the mean, also the standard deviation of this Gaussian distribution before convolving around this image. So now we got a more, let me so more spread out version of the Gaussian, where more spread version of this Gaussian. And we know that when we are smoothing an image with a Gaussian filter, the more we use the sigma, the more we increase the sigma, the more blurrier the image gets, and it is hard to detect the edges in that image. So, but for this shift, what we will do is that we'll sort of take an image and sort of create 8 such variation of image using different, okay, there were 7, I guess, into I. So there are 8 such um, Gaussian filters that we apply to an image and get an octave out of it. And then what we do is that we take this transformed Gaussian past images and we take difference of that. So this is first octave and this is next octave. So we got this 8888 values and we sort of take difference of that and we get this dog or the difference of Gaussian. And it was established earlier in this lecture that the difference of Gaussian is similar to calculating, same as calculating the Laplacian of the Gaussian. So what they do is that they take three layers, and let's say the intermediate layer for which we are calculating this shift. What they do is that they take all the 26 neighboring pixel, and using this 26 neighboring pixel, they try to find. So if that neighboring, so if the center image is more than more the highest out of this all these 26 number, then that is an interesting point or something. So I couldn't recall it correctly, but it involves like all the 26 pixel that is surrounding that. So let's say we're sort of trying to find interesting point in this set. What I'll do is that I'll take a point in this image, and all the uh, pixels surround him will be 8, and all the pixels there will be immediate neighbor to in the top level and the bottom level I'll consider, and it will be cube, and I'll use that to determine if the image is a like interesting point, if the point in the image is the interesting point or not. So similarly, let's say, so this is the like while scaling the the Gaussian filter, and you can see while when we scale it very much, it is deeply blurred now, and these are like these called octaves. This is the first octave, and this is the second octave, and the third octave. As you can see, when we sort of increase the octaves, like increase the value of this lambda, the image of this baby boy is getting blurred. And we use that, and this is the thing that I was telling. This is the called the local extrema detection, where we sort of try to find one point, and we sort of try to find 26 neighbors, and 8 in the same level, 8 above and 8 below, and select key point only if the larger or smaller than, only if it is larger or smaller than all of this neighborhood. So if this the point of interest that is marked in the cross black cross is sort of an interesting point, then we sort of uh, do that by evaluating this point against all these numbers, and this called local extrema detection. And this is one example of that. And second point is like key point localization. So I guess, yeah. So we do that by so what happens is that the point we select as a key point is neither maxima or minima. Sometimes what we do is that we sort of push it towards the maximum minima to make it work, and in this way, like we achieve this key point localization where we're expected to localize the point where this interesting or important characteristics of an image lies. And other two steps are more of coding than just to discuss it mathematically in this session. So what I'll be doing is that in the coding session, I'll be going through all each and every thing like that need to be coded, and it is each and everything that is written in this code, and written on this code. So so we'll discuss this step 3 and step 4 there, where we'll apply this in an image to find the shift edge invariant capability of an image. Okay, so this ends my slides, I guess. Yeah, so this ends my slides. If you have any doubt, you can ask me in the chat, and then we can move to the uh, coding session. And like also like in the coding session as well, we can choose to discuss things related to theory in between. Okay, great. If you have any questions, you can put in the chat. We will take a short 10 minutes, 5 minutes or 10 minutes. In between 5 and 10 minutes, we'll take a short bit of that amount, like for water or bathroom, and we'll meet after 5-10 minutes to continue with the coding. Thank you. Yep. Sorry guys, my computer screen froze in between the presentation. So I was trying to sort of get back to this screen and I couldn't. I guess there is a huge gap of say 40 minutes in our lecture. So we'll try to cover that up later, or I can just take 1 hour online and sort of upload that. There is so sorry that this discrepancy happened. So I'll try to remember this and not and ensure that it did not happen later. And let's just quickly go through the code. So here is the code that is there for the lectures. The GitHub. And let's just paste it in the chat window itself. Yep, and this is the code. This is the link to the code that we'll be discussing today. And this is the notebook that correspond to the week 2 of the course. And if you see, we sort of this is the implementation of this Sobel filter that we discussed a while ago. And this is the implementation of how we can sort of taking an image and sort of applying the Sobel filter to detect the horizontal and vertical edges. So let's just run this and see how see what are the outputs that this Sobel filter is giving while applied to an actual image, and accordingly we can see. So first block is done, and if you see carefully, this is these are all these are all the libraries that we're using. And if you see NumPy is a uh, vectoring library where we sort of see all these things, the arrays and vectors and matrix, and we deal with them. And since we're sort of looking at images or 2D tensors, we can say that we'll use this library a lot. Then we sort of use CV2 and matplotlib. And CV2 is something we use for doing all these images stuff. So when the image increase with domain and time, the size of image is pretty large in the real world. So, and also all these edges and like squares and all these things where it's very hard to detect initially. So all these functionalities are sort of created and embedded into these images. CV2 is a very efficient way to apply all these things to our image. Then third is like so all these uh, libraries now sort of uh, uh, we need. And let us start with converting an image from color to grayscale. Let's say this is the image that we are trying to read. And so we sort of first created the height, width, and depth of this image. Then we sort of create extract the RGB value of it, and uh, and we sort of try to create the try to get the weight of each layers, and we sort of multiplied the so sort of take all these ratios of this each layer and trying to get that, and sort of add every layer to get one single layer, and this will be a grayscale image out of it. It's pretty straightforward. If you just look into the code, you'll be able to get it, or you'll be able to guess what's happening here. Where just is the code for uh, converting this colored image to black and white image. I'll just run that. I don't know, it's throwing error. Please open the URL for reading and pass the result to the below easy NDRL like this. Take this as it is and try to open that like this. We're still getting this error. Let me
It's optional. It's basically matplotlib. We use that particular command. This is, I think, probably some good image and components to one. I think you can just basically go through this. You can use any grayscale, GX, which detects your.
Nope. Should be able to run this, but I'm currently not able to run that. So if you run this, you'll get two images like this, uh, original and the modified. And so this is like applying the Sauber filter, the filter that we discussed in the slide, for uh, finding the vertical and the horizontal edges. And so then we can find like how the image will look after applying the canny edge detector that we saw in the lecture slides. And this is the gray image. This is after doing the Gaussian smoothing. And this is uh, the image after uh, performing this um, magnitude of the gradients. Yeah, so the gradient magnitude. and this is after doing the non-maximums of suppression, where we uh, sort of find these maximum points and suppress all those non-maximum points, enhancing the maximum point, so that we use to sort of make the uh, make this plots make these edges more thinner, sharper, and more specific, uh, uh, as compared to the earlier points. Like, will so the initial algorithm gives us a very thick edges which you do not want. We want the exact edges, so you need to refine that. That's what we did in this non-maximum suppression. Then we use linking and thresholding. So what happens is that when we are sort of trying to figure out the edges, and uh, the link between the two edges might be missing. So to adjust that, we use this linking and thresholding, where we sort of connect all the missing edges, and then we do this history. Then we do this hysteresis, where we do this linking and uh, mixing as well. And after doing all these things, this is our final results, which you can see that clearly describe all those edges that is present in an image. So this is the code of that. Sorry, I couldn't run it, and my computer got frozen for quite some time. I couldn't reply as well. So I'll try to cover this code separately, where I'll run this code step by step and say that what is happening. So before uploading this video to the YouTube, what I'll do is that, so I guess we discussed pretty fairly till 1 hour and 10 minutes, and we discussed the last 20 minutes. So what I'll do is that I will sort of try to create a video of 30 minutes describing this code line by line, and while explaining this code, and I'll sort of merge that to our discussion that we have today, and I'll post this merged video in the chat, merge with the YouTube, and share the link with the NPTEL people, so that you can have a look at this merged video and see. So I'm so sorry I couldn't describe this code to you, and so it will be available in the video as well. So I think this is everything that I wanted to say in the today's discussion. It is already been late, like 5 minutes. So I'll stop my meeting here, and I'll see you guys next week. So if you have any doubt or something, you can just keep it to yourself, or you can put in the chat or discussion forums. I'll take it in the next week. Thank you for all the patience and all the dedication to this lecture. Thank you. Bye.